So, this is the fourth lecture of module 1 of the series that we started on waves in space time and its propagation. Just to recollect what we have done so far was finding out something that we had called the infinitesimal Lorentz transformation. So, the next objective that one should have is the result of this infinitesimal Lorentz transformation on some vectorial quantity that is defined on the space where this transformation actually acts. So, to find that out, the best possible thing is define a quantity in a primed frame of reference, then go from this primed frame of reference to this unprimed frame of reference, or put it differently, I would say, take the vector in the unprimed coordinate system, then act on it the Lorentz transformation matrix, eventually take the transformation to be infinitesimal, and what we should have is the vector in the primed coordinate system. Now, take the difference between the primed coordinate system vector and the unprimed coordinate system vector, and this difference should give us the change that this vector has undergone. If we call this change as delta of A mu prime, then it can be shown that this difference can be written as half the infinitesimal Lorentz transformation parameter epsilon, some index sigma and rho, those vary between either 0 to 3 or 1 to 4, and the Kronecker deltas and the Minkowski metric eta of sigma nu and eta of rho nu multiplied by appropriate factors of delta times the original vector that we had in the unprimed coordinate system that we have shown in equation 5 in bold as A nu. The appearance of this particular factor of a half might be surprising, and what might be little interesting to look into is how does this particular quantities, those appear within the bracket, first bracket. Okay. The factor half that appears there is due to the fact that the repeated indices, when they are summed up, often they appear in opposite order, and to get rid of this extra appearance with the opposite order, we had to divide it by a factor of half. So, ignoring the first infinitesimal Lorentz transformation element epsilon sigma rho, the rest of the tensorial structure can be defined as we have done in the sixth equation, and by defining a quantity that is g of mu nu sigma rho or rho sigma, to write the change in the vector A mu as a product of epsilon and this g. Okay. So, how did we really come to find this expression for g in the form that is given on the right hand side of equation 6? That particular way of coming to this expression is also known as Rindler's trick. That's we have showing it in the present PPT presentation or the Beamer presentation here. First, we note that any mixed tensor, here the mixed tensor being the elements of the Lorentz transformation matrix omega mu nu, one upper and one lower index, can be written as product of the Minkowski metric along with the Kronecker delta symbol involving some other space time indices beta and nu, and a Lorentz transformation parameter, that is infinite symbol omega of alpha and beta. This omega of alpha and beta is antisymmetric in alpha and beta, but what is happening here is the indices alpha and beta, they are dummy indices, that is they are being summed up. So one can in principle add them twice and divide it by a factor of half. In one case, the first case, we retain the indices in their order as alpha and beta, and in the next term we interchange alpha with beta and beta with alpha, and this is what we have obtained in the eighth equation for omega of mixed indices mu and nu. Once we have done this, what we can do next is, in the next step, interchange the position of alpha and beta with beta and alpha. In the second term, in the 8th equation, to generate what is called half of omega of alpha beta, which is common, and there are two pieces. One of them have plus sign that it had from the beginning, and the second one comes with a negative sign that it acquires moment we interchange the locations of alpha and beta. So, the mixed tensor or infinitesimal Lorentz transformation parameter omega of mu nu now becomes equal to half of omega of alpha beta, and then inside bracket something what we had defined in the previous slide by capital G, and probably without loss of much of the generality can call it in terms of m of mu nu. I mean, both of them they just map onto each other. So, at the end, this infinitesimal Lorentz transformation parameter epsilon, it can be written as a product of two quantities. One of them is covariant infinitesimal Lorentz transformation parameter omega of mu nu multiplied by what we have defined as capital M of alpha beta with the indices capital mu and capital nu. And this particular quantity m of alpha beta mu nu is what we call as the generators of the symmetry. Fine. So, our change in the vector a mu now can be defined as a product of two quantities, as we have said already. Those are omega and g, or omega and m. Thank you.